Probably.
We have some as well.
Okay.
So 11 on so yeah. So the integral of x cubed and then the square root of x squared minus 4.
Square root of x minus 4?
X squared minus 4.
X squared minus 4. Okay. Okay. That look right?
Yep.
So we can't do this with the u substitution. Maybe we could. We were clever, but let's do
Don't say that.
a trig substitution. Okay. So if we see a square root of x squared minus something, minus in there, we want the square root of the one preceding is going to be the hypotenuse.
On the right.
And so then we need
2's on the bottom.
2's going to be on the bottom,
Yep.
and that means the radical is going to be here.
Well, that would be one of the things I
What's that?
no, we got it right now.
Oh.
Always put the extra radical on the
Yeah,
right.
I moved my theta because I was too lazy to rewrite the radical. That's what it is.
That was a huge time savings, I'm sure. So the one that connects the x with the constant looks like secant, is that right?
Yeah.
Secant theta is x over 2, so our x is 2 secant theta. So our dx is going to be 2 secant theta tangent theta, d theta. And we need our radical. So we're going to partner that up with our constant, so that makes it a tangent of theta. Is our radical over 2. So our radical is going to be 2 tangent theta. You okay so far?
Yep.
All right, so let's see. Now it gets ugly. The x cubed, we're going to get, should we go 8 secant cubed theta. The radical is a 2 tangent theta.
And then 2z.
And then another 2 secant theta d theta. Oh boy.
And this is what we got.
Let's see, 2, 4, 32 comes out.
2z 4.
Secant to the 4th.
Wait.
And, right, secant times secant cubed.
Yeah, there's another tangent.
Yeah, they
Because dx is secant tangent.
Oh, I didn't want to shortchange it. So it should be a tangent squared.
Can't be having easy problems here, Mr. Street.
I tried to make it easy. Okay, and here's our issue, is how do we do this? So did we check with our little sheet that says 7.3 on it? Did it give us any suggestions?
Not that I could find.
No.
Well, then you have to do power reducing after you convert it to sines and cosines. Which
When they're both even, there's no subtraction.
we have to do power reducing for both even. But
Meaning
because it's
both.
secant tangent, you have to convert it to sines and cosines and then power reduce is the only way I could thought to do it. But I didn't want to do all that work if I was going to be wrong.
Oh,
We
so rather than try it and see if it would work,
I
you
was
said,
running out of room.
we'll have Mr. Street do it.
We switched a secant squared into tangent squared plus 1 and multiplied that out, and that way we could use tangent as a u sub. But
It didn't work.
I mean, it kind of
Why
worked.
did you say
but
that? That seems like it would work better than I was doing.
We just don't, I don't know, a lot
It
of the,
seems like it seemed weird, a little too weird.
Oh, I think that should work.
Well,
Yeah,
yeah,
I like that idea.
Oh yeah, their answer
yeah,
was
theirs was like-
atrocious.
they kept factoring out weird constants and things.
There was a 1/15th at one point.
Yeah, no, that would be a problem, I think, yeah.
Like this?
Mm-hmm.
Let's see, I don't like that idea.
You don't, or you do?
I do. I think, because we say u is going to be tangent, then our secant squared is going to be our du. So we're going to kind of double distribute here, right? So that one integral is going to be 32 tangent to the 4th theta secant squared theta
Once again, you're correct.
plus we're going to 32 then just a tangent squared theta secant squared theta d theta. I think we're in a good place. So for both of these integrals, we can say u will be the tangent. Du, well then there's our secant squared theta d theta. that okay? So we're gonna get a, I'm gonna work up this way. So this is gonna become 32 integral u to the fourth, and all of that is our du plus a 32 u squared du. That look reasonable?
Oh, well, that's not bad.
Ah, if you hadn't been trying to save a piece of paper.
Can I say an activist?
Yeah, that's one way of describing it, I guess. 32, we get 130 cubed. Let's see, is that looking okay? So 32 fifths, RU was a tangent. 32 thirds. Remember, all this started with trig substitution, so we're not done yet.
Okay, that's what me and Colton had, but the answer was atrocious.
Well, because we had to go back here, right?
Oh, no, we did that.
Oh, you did that? Oh, still.
It's still not even close to what they had.
Oh, so tangent is this over that, so
Just
to
keep
the
it as that,
fifth.
to the fifth.
So can we think of that as being x squared minus 4 to the 1/2 to the fifth is 5 halves? And then the 2 to the fifth will be a 32. I think we're going to get a good cancellation. 32 thirds, and this tangent is going to be x squared minus 4 to the 3 halves over 8. We did all this. So we can cancel the 32s, so that's a 1/5 x squared minus, well, I have an idea what they might have done. See, 8 goes into there, 4 thirds, x squared minus 4. They did not have this, right? Is that what you're saying?
They did not.
Did they factor out an x squared minus 4 to the 3 halves, perhaps? And perhaps a least common denominator of 1/15?
They had 1/15, and then parentheses x squared minus 4, close parentheses, 3 over 2, and parentheses 3x squared plus 8.
We got it. We got it.
Oh, I didn't get there.
Yeah, there's no way I was getting there.
Oh, yeah. Oh, yeah. Okay, so it's just, and I'd be totally happy with this. So our least common denominator between fifths and thirds is going to be 1/15. The smallest exponent between these is going to be to the 3 halves. That's what we're going to pull out. So when we factor out the 1/15, it's like we're dividing by 1/15, which means we're multiplying by 15, which is going to make this be 3. When we factor this out, it's like we're dividing by that, which means we're subtracting 3 halves from 5 halves, which will make it now be 1. We factored out the 1/15, so we're dividing by 1/15, multiplying by 15. That'll cancel, be 5 times 4 is 20. We took all of that out. So we'll just distribute and combine like terms.
So, in any point in our life, will we ask to do this again? Like, is there any reason to go further to this?
Well, on this particular problem, I'm not sure it really serves much of a purpose. But the idea of being able to factor out like those least common denominators and the smaller exponents to make it be more compact can be really useful. Like if you have a first or second derivative and you're trying to set it equal to 0 to find critical points or potential inflection points, this form is, because it's all being just multiplied, is much easier to say, okay, I can just set this equal to 0 and that equal to 0 and solve. Rather than when it's being a sum or difference, then it just doesn't work very well that way. So I think there is, I think the process of doing this is useful. I don't know that I would have done it on this problem because it's just about how you're going to write your final answer. I mean, it could be, I couldn't imagine it being anything quite this complex, but they will force you at times on AP test questions, particularly multiple choice questions, to do some simplification and some algebra because you're going to have to find your answer among the multiple choice questions. And they will sometimes make you do some simplification. I don't think it would be quite this involved, but that kind of technique or skill they may want to test. So that can happen. Okay.
We got one more question.
All right.
So we just, like, we did everything, we just don't, like, we got it to the final part. We just don't know how to, like, after you do a power reduction, and you have a 2 theta,
How that affects when you are plugging in.
like, when you plug everything back into it.
Yeah, you can't. So then you have to use, so if you look at that 7.3 worksheet, I'm hoping it was assigned 2 theta that you had to deal with.
Yeah.
Yeah.
On the very top of that, I put in there that double angle formula that sine 2 theta is equal to 2 sine theta cosine theta.
This is on top of the one we got in class.
Yeah, I don't think it's on the one on Canvas.
It's not.
Yeah, do you need one of those?
It did not print that off.
Yeah, but this one, it doesn't have the top part. The sine two theta doesn't have that up.
So if you printed yours off Canvas, I don't think it has that. So either add it to the top or I can give you one that has it.
Is that all that's different?
That's the only thing that's
Okay,
different.
yeah, I'll just write it down.
Okay. Do you have one like that already? So I think it might even come up on a test question. So I think that's why I put it on there originally. So make sure you got it.
Put a fat old star by that film.
Anything else? Okay. So we're going to talk about something today. They're known as hyperbolic functions. And I'm a little torn every year about how much to spend on this because I think its use and application is pretty narrow. So this is stolen from another book. So these are hyperbolic functions. So this, what we're going to do today falls under the category of like kind of exposure. So we're going to talk about this a little bit so that you have seen them before. In the event that you encounter them somewhere, it won't be like, what in the world is this? But you'll be, oh yeah, we talked about that a little bit. I'm not going to test you on it. You won't see it on the AP exam. But in some narrow, as far as I know anyway, some narrow fields, particularly like if you are an engineering that's going to do something with bridges, is the application that I know, then these might come into play there. And to my knowledge, and there might be other applications that probably are, I don't know of others. But we have a definition for it. So we have these things that are called hyperbolic sines and hyperbolic cosines. So they're written as S-I-N-H-X, and that is read either as hyperbolic sine of x or sinh x, which is kind of weird. But it's by definition, it has nothing to do with sines and cosines. It's e to the x minus e to the negative x all over 2. So that's the hyperbolic sine. And the hyperbolic cosine is e to the x plus e to the negative x all over 2. And then once you have a definition for hyperbolic sine and hyperbolic cosine, you can define other hyperbolic functions like you would the trig functions. So you can define so this is sometimes called sinh, and that's sometimes called cosh. I don't know that there's any other clever little names for them. So, and these aren't used as much anyway. But a hyperbolic tangent would be defined as a hyperbolic sine over a hyperbolic cosine, just like we would with trig functions. And likewise, we can do a hyperbolic secant would be 1 over hyperbolic cosine. And a hyperbolic cotangent, which looks like coth, but that's going to be hyperbolic cosine over a hyperbolic sine, and hyperbolic cosecant is 1 over hyperbolic sine. So one of the interesting things is that there's a lot of parallels that happen with trig functions almost. So just like we know that sine squared plus cosine squared is 1, in hyperbolic functions, it's the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. So that's our kind of fundamental identity for hyperbolic functions. Now, the reason for the name, where this comes from, why did they decide to call something with e to the x's in it a hyperbolic cosine or a hyperbolic sine? The reason where that comes from is it's kind of interesting coming from where we are, because we could actually do this stuff using our trig substitutions. So we've done this integral before using an area argument, because do you know what the graph of y equals square root of 1 minus x squared? Yeah, it's a semicircle. And so this is a semicircle with radius 1. And so this integral, if you actually do it, and we could do it now, it's not an easy one, but we could do it using a trig substitution. We couldn't have done it before. It turns out, I'm going to write it below here because it takes a little bit of space. It's going to be 1/2 times x square root of 1 minus x squared, and then we get an arc sine of x. And then, curiously enough, if we do an integral from -1 to 1 of the square root of 1 plus x squared, and that's not as easy to see what the graph of that is. But if we kind of do an aside here, so if we say y is equal to the square root of 1 plus x squared, and if you square both sides, and I don't know if we did enough of this when you were in AP prep or not. Do you know what y squared minus x squared equals 1 is? It's actually what's called a hyperbola. Did we talk about hyperbolas at all when you were there?
I think we may have said the name once.
Okay, so what this hyperbola would look like, so if we were to graph it over here, then we get this thing that is going to look, there's actually 2 parts to this one. It opens up and down. But if we don't worry about this one here, if we go from -1 to 1, so if we look at the area between this one branch of that hyperbola and the x-axis from -1 to 1, which we can now do using trig substitution. But it gets, there's a lot of work to get to what it is. So it's going to be 1/2 times, and we'll get so much like what we got here. It's going to be x times the square root of 1 plus x squared. But then what you end up getting is not the arc sine of x, but the inverse hyperbolic sine. And finding what the inverse hyperbolic sine is not just a walk in the park, because remember, here's your hyperbolic sine. So if you imagine saying y is equal to this, switch the x and y's and solve for the y, it's going to involve logarithms, natural logarithms and stuff like that. So it's not, which we've seen sometimes in one of the integrals we've done, where you end up getting, like when you integrate secant and you get natural log of secant plus tangent, that's like what you're going to see kind of over here, which is the inverse hyperbolic sine of x. So that's where the name comes from, is because these integrals are so similar looking. It's kind of interesting. So if you get bored one day, you can try to see if you can do that. Show that that's really true.
No. Take your word for it. I'll do the same.
There's your sense of adventure. Okay, so here's what we can do. So we can do, now we get some great derivatives. So as you might imagine with things that are defined with e to the x and e to the negative x. So it turns out that the derivative of sinh, and if you're thinking like a trig function, you might suspect it's going to in fact be the derivative, it's going to be cosh, the hyperbolic cosine. And in a sense, it's even better than the trig functions, because the derivative of a hyperbolic cosine is not even the sign change. It is just a hyperbolic sine. So we can, some things we can do, that you'll see like in your homework, is can you do a chain rule with a, say, hyperbolic sine? So just applying some of your calculus knowledge to a new and different function. What's that? We can do this, huh? So what would that be? Okay, not too bad. If we want to take the derivative of, say, the natural log of hyperbolic cosine,
Is that just, is that going to be tangent?
so
Yeah, it would be.
It would just be tangent.
hyperbolic tangent.
Hyperbolic.
So you get 1 over u, so you get that hyperbolic cosine in the denominator, times the derivative of u, so the derivative of hyperbolic cosine is a hyperbolic sine. And we know sine over cosine is tangent, so a hyperbolic sine over a hyperbolic cosine is a hyperbolic tangent, curiously enough. So if we have the derivative of, say, x hyperbolic sine minus hyperbolic cosine, we got a little product rule.
X.
I was like, no, and then I looked back and realized that the hyperbolic signs cancel.
So you got a product rule, so you have the first times the derivative of the second, plus the second times the derivative of the first, and then that would just be a minus hyperbolic sine, and that's going to be our answer. We could do an integral of hyperbolic cosine of 2x hyperbolic sine squared of 2x Do a little U substitution there. So we call U hyperbolic sine of 2x. So du will give us hyperbolic cosine 2x times another 2 from the chain rule derivative. So our dx will have 2 hyperbolic cosine 2x's. So that's going to become u squared du with an extra 1/2. Does that look okay? So that'll become 1/2 times 1/3 u cubed. So 1/6 hyperbolic sine cubed of 2x. That's a constant going up. So let's, we can graph these on our calculators. Our calculators actually have a hyperbolic sine and a hyperbolic cosine function. But you have to go to the catalog. So people that are in, I think, AP Stats, you have more experience doing this. But so if you've not done this before, to find the, use the catalog feature, you go seconds and then 0 is the catalog. There's a long list of functions there. If you hit like the C, so since it starts with the hyperbolic, it starts with a C. If you hit like program where the C appears, it'll take you right down to the beginning of the C options. And then if you scroll down, oh, I should have done y equals first. Let's go y equals first, because we want to put it in a graph. And then go to our catalog, and then to C's, and then scroll down until you can find a hyperbolic cosine. See it? Finding it? And then if you just hit enter and put in x, and then if we do a zoom 6 for a standard window, it looks very much like a parabola. Now, and this is the one really application that I'm aware of. So remember, the hyperbolic cosine was the e to the x plus e to the negative x over 2. So you can see the numerator, these are never going to be negative. So this will never be equal to 0, which is what you're seeing there. When x is 0, you get 1 plus 1 is 2 over 2 is going to be 1. But then you can, you can stretch this and do all those things. So that shape, which looks like a parabola, that is actually called a catenary. That shape is known as a catenary. And so it is what happens in like nature, or if you've ever, like when you drive down the highway and you see, those power lines. I don't know if you've ever noticed and thought, man, that sure looks like those are like really flattened out parabolas because gravity's kind of pushing it down. In fact, these are not parabolas, they're actually catenaries. So the shape that you get with something just hanging and gravity acting on it is not a parabola, it's a catenary, something that's one of these things, a hyperbolic cosine. And so if you've ever seen, like, I don't know if you've been out to San Francisco and seen like the Golden Gate Bridge or something, those are called suspension bridges. They have these big thick cables that then suspend like parts of the bridge there. Those are called suspension bridges, and these shapes, these are catenaries. And so that's, I think if you were in a design of a suspension bridge, you would certainly do a lot of work with hyperbolic cosines. And I don't know where else it would come up. That's the only thing that I've heard of there. So if you graph hyperbolic sine, now remember, hyperbolic sine is going to be 0. So your hyperbolic sine is that e to the x minus e to the negative x over 2. So at 0, it's going to be 0. So this is going to go through the origin. So should we maybe go back to y equals, if you clear that one off and then go back to catalog, and now we can go S, which is, that's the LN button, and then scroll down till we can find hyperbolic signs of x. Yeah, it looks a lot like a cubic, but it's not a cubic, so. Okay? So, here is a little bit of an application of.
What is this one called? Is this also a catenary?
I don't know what that shit. I don't know that it has a name, to be honest with you. I don't know if there's anything special about that. I don't know. So, let's say that power cables are hung from 2 towers. So power cables are hung from 2 towers, forming a catenary. The distance between the towers is 2b. The distance between the towers is 2b. Find the slope of the catenary. Find the slope of the catenary. Where the cable meets the right-hand tower. I'm going to give you a picture with this. The right-hand tower. So we've got, here's our scale. We've got these towers. I'll have an opportunity to use my artistic skills. And we'll say that this distance is b, and we're over here at negative b, and that our catenary is going to hang down kind of like that, and that this is going to be our distance a, and that the equation of that catenary is going to be the hyperbolic cosine of x over a.
Oh, A equals, okay.
Okay. So, trying to find the slope, where?
At B.
At B. And the slope is given by?
What from? Sine H.
Sine evaluate that at?
Negative b. No. No, just that.
Just
Just a b, yeah. So it would be. Okay. So let me, I want to give you these printouts because there's some information in graphs on here. These are all available on Canvas as well. So we have a couple of them. This is where your homework will come from as well. So on that front page, you can see kind of what we talked about there. The graph, you can see the y equals square root of 1 minus x squared, the semicircle, the hyperbola, and how that area comes from how the reason they're named what they are has to do with the fact that when you try to find the area between the curve and the x-axis, you end up with these things involving arc sine and an inverse hyperbolic sine. You can see there are definitions of all those on that page. If you flip over, there's some graphs of each of those different hyperbolic functions. Kind of interesting looking graphs for some of them. And they walk through on the bottom there why the hyperbolic cosine squared minus the hyperbolic sine squared is in fact equal to 1. If you flip over to the next page, so I think it says 397 now, there's some identities, and they're gonna, some of your homework problems may ask you to verify some of these. We'll try to do an example of that in a minute. It tells you their derivatives, but they're not too surprising there. These are not ones that you're gonna have to memorize. I'm not gonna test you on that. And then after that, you can see the different homework problems. So let's do a couple kind of problems like what you might see in your homework here. So if we know that the hyperbolic sine is 5/3, can we find the hyperbolic cosine? Ideas of how to do that.
We set the 5/3 equal to the e to the x minus.
That might be a thought. It might be pretty tough, though. I think what we want to do here is think in terms of that fundamental equation.
Square.
Remember what that one is?
Sine squared.
Yeah.
Minus
Cosine comes first. Yeah. Okay.
Square root of that is
Plug in this.
And then plug in the 5/3 for that.
We have the one.
which means you get 34 times is equal. Oh, so you got a square root. So you get the square root of
It's going to be a positive or negative.
Positive. No.
good question.
Remember our definition for hyperbolic cosine? Do you remember it?
Oh, it can't be negative, so positive.
Can't be negative. It says e to the x plus e to the negative x over 2. So when we take the square root of this, we'll only keep the positive one. It couldn't be a negative.
Can sine be negative?
Yes.
Sine is only,
If you have a.
no,
Yeah, because it has a minus sign in it, so it could be positive or negative.
So yeah.
So then we have one that says verify the identity. And the identity is that the hyperbolic cosine squared of x is 1 plus the hyperbolic cosine of 2x all over 2. Kind of like our power reducing formula there. So we don't do much of these in AP Prep anymore. It kind of got sacrificed when I tried to put in parametrics and polars and vectors and that stuff that we do in AP Prep. But the idea behind an identity is it's really like a proof, a mathematical proof. So what you're supposed to do is take one side and just work it until you can make it equal to the other side. But you can't like multiply both sides of the equal sign. You can't change both sides of the equal sign. You can only work with one side or the other until you can make it look like the other. In general, you want to take the more complicated side and make it look like the simpler side, because in general, it's easier to uncomplicate things than to complicate them in the right way.
With the equation that you wrote at the top of R 7.3, does that work with?
But there is one that's comparable to that, and so that's exactly where we want to start. So just like we had that identity that we put on the top of our 7.3 sine 2 theta is 2 sine theta cosine theta. If you look on that page, is it 397? Then there's a cos somewhere down there. Where do we? Cos is, yeah. So we're going to call it, say it's going to be cos is it squared?
Yeah.
Plus sin squared. Does that look right?
There's no one, no. It's
The one's coming from here.
Oh, I was doing it the other way. Yeah, sorry.
Is that okay?
Yeah.
All right. Any brilliant insights?
Split it up.
Wait, are we allowed to use the equation in solving the equation?
No.
Oh, 1 plus sin squared
There you
is
go.
cos squared.
Or we could just replace the 1 by cos squared minus sin squared, either one, yeah. So we could do that. So what? So if we do that and see that you want to trade the 1 plus cos squared, no, it'd have to be
So
1 plus sin squared would be cos squared, is that right? So these two will become a hyperbolic cosine squared plus the other one we have. And then we're there. And we have proved what it is we set out to prove. Good. Okay, well, that's what I wanted to do. We got about 6 minutes. Anything we'd like to do should we try doing some huge logistic growth differential equation and sort our way through how you would solve that? It's been a long time.
We can do it.
Okay, so if we say that dp dt is equal to say 0.0, I could be in trouble making this up off the top of my head like this. 100 minus p. I don't have any idea if that's going to work. And we can make up an initial condition. We'll say p of 0 is going to be, say, 10. And we're going to try to solve this for p.
You kissed it. Yeah. Are we going forward?
I think we should.
Oh yeah. I'm taking the green.
Taking the blue. So like you're 1 100, you get to here. Okay. Well, I don't stick this stuff. You get so over here. And so you have that minus. You forgot your paper again. So then you get equals that side. And then you have to multiply everything by negative 100 so that this. Multiply everything by negative, and that helps this. So you get to here. Exponentiate everything.
Extraordinarily complicated.
Once you get to here,
Somewhat.
it's kind of nice. Then you can
Larry?
solve for the C.
Larry.
Larry's is 9. And then you just take the reciprocal. of everything.
And was that yesterday?
No, this was the test. This was like last Monday. I'm gonna have to redo the review again. Yeah, we just did this.
We ran out of time for the initial condition, but
You didn't mess up Larry, how dare you?
I didn't see him.